In question 2, we are given the equation of the derivative and asked to find critical points and then identify local minimums and local maximums using our derivative tests. Now, I think a little bit some people just got confused with the way the problem was written. The purpose of this was actually to make life easier on you. If you notice, there's an equal sign right here. So basically, you're given the derivative equation in factored form as well as in its expanded form. So you didn't need to waste time distributing it at all. But for the first part, I'm going to actually focus on the factored form because the factored form is going to be more helpful to me. So we're asked to find the location of all critical values. Now, if you remember, there are two places where critical values might occur on a function. They're going to be where my derivative h prime of x equals 0 or where h prime of x is undefined. Now, this is a polynomial function. It's never undefined. It exists. Its domain goes from negative infinity to positive infinity. So that means that this second piece, we're not going to need to worry about that today. So we're only looking where our derivative is equal to 0. So I'm going to set up that equation. We have 0 equals x cubed times 2x plus 6 times 5 minus x all squared. Now, the reason why factored form is going to be so helpful to me here is the zero product property. If you remember back from Algebra 1, Algebra 2, if any one of these factors, so the x cubed or the 2x plus 6 or the 5 minus x squared is 0, then the whole expression would go to 0 because if I multiply by 0, the answer is 0. So basically I need to create three sort of mini equations. One equation would be the 5 minus x squared equals 0. And then I would have the 2x plus 6 equals 0. And then last but not least, x cubed equals 0. And if I solve these three equations, they're going to tell me where my critical values occur. So x cubed is going to be 0 when x equals 0. It's not too bad. This middle one takes a little more work. So we have 2x plus 6 equals 0. So I could subtract 6 to the other side and say 2x equals negative 6. 2 times negative 3 would equal negative 6. So x equals negative 3. And then last but not least, I have this 5 minus x squared equals 0. Well, the squared doesn't really impact anything because 0 squared is 0. So I really just have 5 minus x equals 0. That's what I'm trying to solve. And so x would be 5 in this case. And so I have three potential critical values on my graph. I have x equals 0, x equals negative 3, and x equals 5. And this would be a good point to pull up Desmos and double check that you did your algebra correctly. So I'm going to do that right now. So I have ready for us in Desmos the graph of the derivative. And if you notice on this graph, we have three zeros. We have a 0 at negative 3, a 0 at 0, and a 0 at 5. All right, I found the critical values. There are no other zeros. So I'm going to go back now and see what I'm asked to do next. So the next question says, I want to figure out the locations of my local minimums using the first derivative test. The first derivative test basically says, okay, minimums have to, or maximums have to occur at critical values. And to be a local minimum, so, we know we're looking for places where h prime of x equals 0. And that h prime of x would need to change from negative to positive, because that means the graph of h would be going from decreasing to increasing. All right, the easiest thing to do here is to make yourself a sign chart. So when I make myself a sign chart, what I do is I draw myself a little line. I like to put arrows on the end. I label it with the derivative whose sign I'm looking at, so h prime of x. And then I label all my critical values. So 0 is going to fall in the middle. I have a -3 over here, and I have a 5 over here. And now basically I need to figure out, is my derivative positive or negative between these numbers? So going back up here, I'm going to start over here to the left of -3. Now I need to pick a number that's smaller than -3. So something like -4. And if I go through and I sort of say, okay, well, -4 cubed is going to be negative. So I have a negative number. And then 2 times -4 would be -8, plus 6 is going to result in another negative number. But this 5 minus x, whatever it is, and if I'm square, it's going to be positive. So if I have a negative times a positive, I'm going to end up with a positive value. So notice I didn't actually come up with the value. I just was checking in my head, did that value come out positive or negative? All right, then I do it again between -3 and 0. So if I plugged in -1, so -1 cubed would be negative. 2 times -1 would be -2, plus 6 would be positive. So I'm getting a positive number out of that second factor this time. And my last factor is always going to be positive because of that squared. So I have a negative times a positive number times a positive number should result in a negative number. And then I keep repeating. So I need to check, okay, at 0, do I flip to increasing? So if I plug in 1 cubed is positive, 2 plus 6 is positive, and then positive. A positive times a positive times a positive stays a positive value. And then again at a number bigger than 5, going to result in another positive number. Now, these signs I could also check with the graph. So if I'm looking at the graph of the derivative here, notice to the left of -3, my derivative is positive. Then between -3 and 0, it's negative, and then it remains positive the rest of the function. And so that sort of values are reflected on my sign chart. And I can look here and I can go, okay, my function's increasing, then it's decreasing, then it's increasing, and then it's increasing some more. I like to draw that in because then even with my little arrows, I can sort of see, oh, at -3, that's not going to be a minimum. That's probably going to be a maximum. That is going to be a maximum. And then here at 0, I'm going from decreasing to increasing. And so I hit a low point. And 5, I have neither. So if I want to then go and justify and answer this question, always make sure I'm answering the question. I want the x coordinate of the local minimum. So I have a local min at x equals 0. And I'm justifying with the first derivative test because h prime of 0 equals 0 and h prime of x changes from negative to positive. And that's it. I've justified with the first derivative test and found the location of my local minimum. Question C is now asking for a local maximum. Now, here's the good news. You already know the x-coordinate of the local maximum. You found it on the previous question. The only thing that you have to sort of add in addition is it's now asking us to justify with the second derivative test. So a reminder about the second derivative test. The second derivative test is looking at concavity and using that to help me determine if I have a min or max value. So to prove a local max with the second derivative test, first off, I need to have shown that h prime of x equals 0, which I already did. And then to be a maximum, think about what a maximum curve looks like. In order to reach a high point, I hate that it auto-fixes lines, but we'll do our best. So to get a maximum, we're going to have a concave down graph. So that would mean h double prime would need to be less than 0 at that x value. So if I can show those two things, I can prove that I have a local maximum. So I know that it's not going to be at 0 because I ruled that out. I made that's a local min. I found that on the last test. And I used the first derivative test to show that 5 is probably neither, which means -3 is the point I'm interested in. And according to the first derivative test, it should be a local max. So let's just prove that with the second derivative test. So I need the second derivative. And this is why we were given way back at the beginning of the problem, the factored form or the distributed form of this problem. So we're going to now want to use this to find the derivative because it's easier to do power rule than product rule. So we want to find h double prime of x. And so I'd get 12x to the 5th minus 70x to the 4th minus 40x cubed plus 450x squared. And if I were to plug in 3 into this function, and I would do this in a calculator, I come out with a negative 3,456. So that's obviously less than 0. Earlier in part A, I know that h prime of 3 is equal to 0. And so I have a critical value. My function is concave down. Therefore, there is a local max at x equals, oops, that should be -3. It helps if I put my sign at x equals -3 because h double prime of -3 is less than 0 and h prime of -3 equals 0. That's my second derivative test justification. Now, again, I can check this in Desmos. So if I were to go back to my Desmos graph, maybe I'm going to actually name this. We'll call it f of x. Oops. And let's say I was struggling finding the derivative. Remember, we can have Desmos find derivatives for us. If we type in our prime notation and I say f prime of x, and so now I have my second derivative graph here shown. And if I go towards -3, I'll notice that my graph is negative there. So my function of h must be concave down there. Since it's concave down and I have a critical value at -3, it must be a maximum. So this is a great problem that shows how we can use technology to double check our answers while still supporting our work with the calculus and the ideas of what makes a min and a max value. And that's it for the second problem on the quest.